In Chapter 15, Section 1, we're going to look at double integrals using rectangles. So in the first problem, we actually don't have to do any arithmetic. We just have to look at a picture and decide what we think about it. So it gives us a function, x and y, so it's three-dimensional, and it says use these rectangular coordinates and compute the Riemann sums. It says without using any calculator. So V is going to be the volume of the actual solid, and then L is going to be using a lower left corner, and U is going to be using an upper right corner, respectively. Okay, so here is the picture. So this is what the surface looks like. So it's half of a ball, basically half of a sphere. And so to find the different Riemann sums, we would have to draw little rectangles. So there's two ways to draw these rectangles. You go up to the surface and you go over and down, and then you get that area. Or so that would be completely underneath the dome, and so that area would underestimate a little bit, and this is the right corner estimate. So that's going to underestimate the volume a little bit. It's kind of hard to draw. Let me see if I can get this shown better. Yeah, maybe like this. Okay, so it's completely underneath the dome. If I do a left estimate, I go up and come to the left, and I go outside of the dome a little bit. So I get a little more area. Okay, so that's going to overestimate the volume of the dome. So we go back to our choices and we say the upper right corner underestimated, the upper left corner overestimated, so the best estimate in order, or I should say from small to big, would be the left estimate, and then the actual volume of the sphere, and then the right estimate. If I've said that correctly, let's see here. Oh, L is lower left corner, and U is the upper right corner. So I drew it correctly, and so that would be the order of small to big in estimation. Okay, so for problem 2, this is where we'll actually start to do these double integrals. So we have so it gives us a set of x's and a set of y's. And so we're going to have the integral from, we're going to do x and then y first. So the y coordinates are 2, 7. Then the x coordinates are -3, 3 of 4, and dA we're going to write as dx dy. So there's two ways to do this. Or we could have done it with x last and y first, and then it would be 4 dy dx. So notice that the order of these numbers matches the order of integration. So if my x terms 3 and 3 are first, I have to write dx first. If my y terms 2 and 7 are first, then I have to write dy first. And we should get the exact same answer. I'm only going to work one of these, but you can work the second one if you want and prove that it's the same. Okay, so we have 2, 7. The antiderivative of 4 would be 4x, and we're evaluating that from -3 to 3. And then we have dy. Well, this is going to be 2, 7 times 4, substitute the upper limit of 3, minus 4, substitute the lower limit of -3, all on, and still inside of dy. This is going to be 2, 7, that's 12 minus -3, so another 12 dy. So this is really the antiderivative of 2, 7 of 24 dy. And the antiderivative of 24 would be 24y, and we're evaluating it from 2 to 7. So that's going to be 24 replace y with 7 minus 24 replace y with 2. And if you do that, you should get 120, which is what we have right there. Okay, so that would be problem number 2. Problem 3, they give us an equation and they say just do dx or dy. So they say f of xy is equal to y plus x e to the y. And in the first one, they want us to go from 0 to 2 of that function with respect to x. So we have y plus x e to the y with respect to x. Now that's going to equal, y is just a variable now because we're taking the antiderivative with respect to x only. So y is just like a number, just like a constant. So the antiderivative of a constant is just add an x on it. The antiderivative of x would be x squared over 2, where ey is the constant. And we want to evaluate this from 0 to 2. And we're only replacing the x's with that number. So we're going to get 2y plus 2 squared over 2 ey. That's the 2 substituted, now the 0, which would be 0 plus 0. So if you simplify this, you're going to get 2y plus 4 over 2, which is 2 e to the y. And that's what we get right there. Okay, in part 2, they want us to do that same function, but we're going from 0 to 1, and we're doing the y term now. So we're going to get the antiderivative of y to the first is y to the second over 2. The antiderivative of ey is ey with an x on it. And we're going from 0 to 1. So that's going to equal 1/2 plus x e to the first minus 0 over 2 plus x e to the 0. And e to the 0 is a number, it's 1. So we're going to get 1/2 plus x e to the 1 minus x times e to the 0, which is 1. So we get 1/2 plus xe1 minus x, which is right there. That's problem 3. Moving right along. Okay, problem 4. Very similar. They give us the order of integration. And honestly, let's not write all this. Let's just break this into chunks. I'm just going to look at this antiderivative all by itself, not even consider the outer antiderivative. So let's just calculate from 1 to 3, 16x cubed minus 18x squared y squared dy. So y is the variable. So this is going to give us 16x cubed y minus 18x squared y cubed over 3. And we're valuing that whole thing from 1 to 3. And so we're going to get 16x to the third times 3 minus this 18 and 3 can be written as 6x squared, and then it's 3 to the third. Okay, minus, now plug in 1. This would be 16x cubed minus 6x squared times 1 cubed, which is just 1. So we're just going to have that. And if you distribute these 3's and combine like terms, you should get all of this will equal you will get this is equal to 32x cubed minus 156x squared. But that is now going to be integrated again, so all of that green circled part will be replaced, and now we're doing the outer antiderivative from 0 to 2 of dx. So that is going to equal 32x to the 4th over 4 minus 156x to the 3rd over 3, and we're valuing that one from 0 to 2. So we'll get 32 divided by 4, which is 8, 2 to the 4th, minus 156 divided by 3 is 52, and it's going to be 2 to the 3rd, minus 8 times 0 to the 4th, minus 52, 0 to the 3rd, but this whole second term is just going to become 0. So we get 8 times 2 to the 4th minus 52 times 2 to the 3rd, and if you do that correctly, you should get negative 288. So these are kind of nice because they do simplify to just numbers. Okay, problem 5. Let's again just do this one chunk at a time. So let's do this derivative first, the inner derivative, 0 to 1, 2x plus y raised to the 6th dx. Now, unfortunately, you can't do this antiderivative without something that we call u substitution. So we're going to let u equal everything in that bubble. Therefore, the derivative of u would be 2 dx, and y would go away. And then we divide by 2 to solve for dx. And so the derivative is going to become 0 to 1, not of this bubble to the 6th, it's u to the 6th, and dx is going to be du over 2. So we're going to pull out that 2 and call it 1/2 0 to 1 u to the 6th du. Now this antiderivative would be u to the 7th over 7. And we're going to combine that and call it 1 over 14, and we're going to replace u with what it was, 2x plus y raised to the 7th, and we're evaluating that from 0 to 1. And keep in mind that I'm only replacing the x with these numbers. So this is going to be 1 over 14 times 2 plus y raised to the 7th minus just y, because x goes to 0, to the 7th. And now that is going to be what we're going to take the antiderivative of for the last part. So the outer antiderivative says evaluate the y term also from 0 to 1. So we have 0 to 1 of, let's pull the 1 over 14 outside of the antiderivative, and we're going to have 2 plus y to the 7th dy. I'm going to make this into two antiderivatives, you'll see why. Minus 1 over 14 antiderivative 0 to 1 of y to the 7th dy. The reason I'm going to do that is because I have to use u substitution again. So now we have to say let u equal 2 plus 7, and therefore du equals, not 7, it should be y. I wrote 7. U is 2 plus y. Du is just dy. So this first term would become 1 over 14 antiderivative 0 to 1 of u to the 7th du. The second derivative over here is, we can do it right away, y to the 8th over 8. And that's being evaluated from 0 to 1. This one, however, we have to do the u part. So it's going to be u to the 8th over 8. And then we're going to change that to back to what it was. 1 over 14 times 1 over 8 is 1 over 112. So we get u to the 8th over 112 minus y to the 8th over 112. And they're both being evaluated from 0 to 1. Now I have to be real careful here. Technically that's not correct. you have to change u back to what it was to use those limits. So this is 2 plus y to the 8th over 112 minus y to the 8th over 112 from 0 to 1. This will be 3 to the 8th over 112 minus 1 to the 8th over 112 minus, plug in 0 now, that's going to give us 2 to the 8th over 112 minus 0 to the 8th over 112. Now that last term will go away, but you're going to have to take 3 to the 8th over 112, 1 to the 8th over 112, 2 to the 8th over 112, and subtract them and add them properly. And if you do that, you will get so you're going to end up with 3 to the 8th over 112 minus 1 to the 8th over 112 minus 2 to the 8th over 112. I shouldn't be writing this 112 in all. I should just write one numerator over one denominator, but that's okay. If you do this, you will get 394 over 7. Just making my life harder because I'm writing more than I need to, but you'll still get the same result. Okay, and that's problem 5. Okay, problem 6 is where we're going to have slightly more interesting approach. So there's a hard way to do, there's an impossible way to do this, and then there's an easier way to do this, or I should say the only way you can do it. So if you do x first, you will not be able to get this one right. So we're going to do y first. So we're going to separate this. We're going to call this the integral of 4. Let me get this right. Let's see, x goes from 0 to 5. And I'm going to pull out 4, 1 plus x squared. And then we're going to have the y term, which goes from 0 to 1. And what's left? We have 1 over 1 plus y squared. And we're doing dy dx. So take a look at where I started and see if you can see what I did. If we're doing the antiderivative with respect to y, then 4 and 1 plus x squared are all constants that can come out of the antiderivative. So I stole the entire numerator out of the antiderivative. That does leave a placeholder 1 in the top part of the numerator. Now you might recall the derivative with respect to y in this case of arctangent of y is 1 over 1 plus y squared. Therefore, the antiderivative of 1 over 1 plus y squared, the antiderivative of 1 over 1 plus y squared with respect to y would equal the arctangent of y. So those go either way, back and forth. So we're going to get, this is going to be, the outer derivative stays like it is, 4 1 plus x squared, and this whole thing becomes, so this is times the arctangent of y evaluated from 0 to 1, and then we have the dx. Okay, arctangent, this would be 0 to 5, 4 1 plus x squared. This is going to be times the arctangent of 1 minus the arctangent of 0 dx. Now arctangent of 0 is 0, so that's nice, it's going to go away. And arctangent of 1, you can type this in your calculator, is pi over 4. So this is pi over 4. So we're going to get that whole antiderivative would just simplify to pi over 4, but it's times 4, so we're going to get, this is the antiderivative of 4 times pi over 4 times 1 plus x squared dx, and that's from 0 to 5. This 4 and 4 will cancel. Pi is a constant, can come out of the antiderivative. So we have 0 to 5, 1 plus x squared dx. That's going to equal pi times x plus x3 over 3 from 0 to 5. This is going to be pi 5 plus 5 cubed over 3 minus 0 plus 0 cubed over 3. Which means the only thing that's going to be left over is 5 plus, so this is going to equal pi times the quantity 5 plus 125 over 3, which is 15 over 3. Added to the 125 would be 140 times pi over 3, 140 pi over 3. So that would be the answer there. If you try to do x first, I guess you could do it, and you would call 4 over 1 plus y squared a constant and pull that out, but I think it might be a little messier because no matter what, you're going to have arctangent at the end. So I believe you could still do it the other way, but I think you might find it a little simpler to go this way that I did. Okay, problem 7. Find the volume of the solid lines under the plane and above the rectangle. So we have to first solve for z, and it's going to be 12 minus 3x minus 2y. And then they give us x and y, and I don't believe it really matters which order you do. I think I did x first. Tend to do x first. It just seems, I don't know. That tends to be what people do. So minus 2 to 1, 0 to 1, and we have 12 minus 3x minus 2y. First we do x, then we do y. So this is going to be minus 2, 1. Antiderivative of 12 would be 12x. Antiderivative of minus 3x would be minus 3x squared over 2. And then minus 2y would just get an x on it. And that goes from 0 to 1, dy. This is going to give us minus 2 to 1. Plug in 1 for x, so we get 12 minus 3 halves minus 2y minus, plug in 0 for x, yep, and every term goes away. So 0 minus 0 minus 0 dy. So now we have the antiderivative of minus 2 to 1. 12 minus 3 halves will turn out to be 21 halves minus the 2y, and everything else has gone away, so it's with respect to y. This is going to equal 21 halves times y minus y squared from minus 2 to 1. So we get 21 over 2 times 1 minus 1 squared minus, plug in the minus 2, 21 over 2 times minus 2 minus minus 2 squared. And again, I'll leave the intermediate algebra steps to you. If you do this correctly, you should get 69 over 2. Problem 7. Okay, problem 8. Find the volume of the solid that lies under the elliptical paraboloid x squared over 9 plus y squared over 16 plus z equal 1. So what we want to do is have now this is an elliptical paraboloid, which means it's going to be symmetric about the x and y axis, and we're going to use that to save us a lot of work. So we're going to have the antiderivative of solve for z, it would be 1 minus x squared over 9 minus y squared over 16 and I did dx dy. Now x goes from, so this is x0, this is x1, this is y0, this is y1. So x goes from -1 to 1, and y goes from -2 to 2. But you can have that and double the integral if this is symmetric, which it is. So we're going to call this 0 to 1, but double this integral. So it's basically, since it's symmetric, we can do half of it and then just double it, double that volume, and we'll get the same, or area, and we'll get the same answer. Same with y. We're going to go from 0 to 2 and double that. The reason we want to do that also is because 0 is super easy to work with. When you plug it into the antiderivative, things just drop away. So it's easier to work with. Okay, so let's look at this. We're going to have, these twos will combine and we'll get 4, 0 to 2. And then let's perform this antiderivative. This would be x minus x cubed over 27 minus xy squared over 16. And we're evaluating that from 0 to 1. And then we have dy left over. So we plug in 1, which is really easy to work with also. We're going to get 1 minus 1 over 27 minus y squared over 16. And that's dy. Okay, and we're going to get 1 minus 1 over 27 would be, let's see here, so this would be 4, antiderivative of 0 to 2 of 26 over 27 minus y squared over 16. We can actually perform this antiderivative. This would be 4 times 26 over 27y minus y cubed over 48. 3 times 16. And that is being evaluated from 0 to 2. So this is going to be 4, 26 over 27 times 2 minus 2 cubed over 48. And that's minus, the 0 term is going to kill everything off. So it's going to look like that. And if you do this correctly, you will get 190 over 27. And that's problem 8. Okay, problem 9 has a slightly different twist to it. They want the average value of f over the given rectangle. So what we have is the f average formula is equal to 1 over the area of the rectangle that they give us times the antiderivative, the double integral I should say, over the region of the function with respect to x and y times the derivative of the area. Okay, so in this one, they give us the area goes from, where is it? It has vertices minus 1, 0, minus 1, 4, 1, 4, and 1, 0. So let's put in those dots. So it says it's got a dot at minus 1, 0, minus 1, 4, 1, 4, and 1, 0. So the region is this box here, this rectangle. That's the region R. Okay, so we're going to get f average equals 1 over the area of R. Well, let's find that real quick. The area of this region would equal, notice the x length is really 2 and the y length is really 4. So we have 8. So the area is 8. And let's do dy dx again. And so we have the y's go from 0 to 4, and the x's go from minus 1 to 1. And the equation they gave us was 3x squared y. 3x squared y. And I said let's do x first, then y. Actually, it doesn't matter, but that's just the way I chose. Okay, so f average will equal 1 over 8 from 0 to 4. The antiderivative with respect to x would be x cubed y from minus 1 to 1, then dy. So this is going to equal 1 over 8, 0 to 4. Plug in 1, you will get y. Plug in minus 1, you'll get minus y dy. So this is equal to 1/8 antiderivative 0 to 4 of negative, it'd be positive, 2y dy. And we'll pull out that 2 and write it over 8. And so it's just the antiderivative of y itself, dy. So this is 1 over 4. The antiderivative of y is y squared over 2 from 0 to 4. 1 over 4 and 1 over 2 can combine to be 1 over 8. And it would just be y squared from 0 to 4. So we get 1 over 8, 4 squared minus 0 squared, which would be 1 over 8 times 16, which is 2. So the antiderivative of that rectangular region applied to that surface, 3x squared times y, the average value of that would be 2. Okay, last problem. Use symmetry to evaluate the double integral. So we have a very similar type problem. I believe I did y first. Yes, let's do that. So we did okay, so if we do y first, all x values can be thought of as constants. So we can pull out 9x over 1 plus x4, and we're just left with y. And then we're going to have dy dx. The y goes from 0 to 1, and the x goes from minus 4 to 4. So we're going to get, first off, we're going to double this and call this 0 to 4. And we're going to get 9x over 1 plus x4. This antiderivative would be y squared over 2 from 0 to 1 dx. But this 1 over 2 and this 2 will cancel, so we're just left with, I'm going to pull the 9 out front, 0 to 4, x over 1 plus x4 of y squared, which would be 1 squared minus 0 squared once we plug in the limits, dx. And that's not going to change anything, so that 1 squared won't do anything. So the real integral we're trying to solve is this one, 0 to 4 x over 1 plus x4 dx. And the reason we wanted to get rid of that y is because this is still a challenging integral. And if we have y's floating around, it makes it even harder. So now the y is gone, and we can focus on this one. Okay, to solve this one, we're going to let u equal x squared. And therefore, du equals 2x dx. And then you solve for dx by dividing du by 2x. So what we're going to get is we're going to get 9, 0 to 4, x over 1 plus x4. Well, if u is x squared, then u squared is x4. So this is really u squared. And then dx is really du over 2x. And I have to get this, if I didn't do this right, this won't work. I have to get all x's to go away. So this is going to be 9 over 2, bring this 2 in the denominator all the way out, 0 to 4 of 1 over 1 plus u squared du. And we just saw this one earlier. 1 over 1 plus u squared is arctangent. So this is going to be 9 over 2 arctangent of u. And I have to substitute in what that is before I put the limits on it. U was x squared, evaluated from 0 to 4. So we're going to get 9 over 2 arctangent of 4 squared minus 9 over 2 arctangent of 0 and I just realized they want us to use symmetry in a different way on this problem. They did not want us to change the limits of integration. So I'm going to go back, and instead we're going to say, no, this is not 0, it's negative 4. But recall that we doubled this when we did that, so this would really be 9 halves, not 9. And then when we pull out the 1/2, this is 9/4 now, and this is still minus 4. This is 9/4, this is 9/4, and this is still minus 4. And what you get is 9/4 and 9/4, but you get minus 4 squared. So we get in this bubble, it should be minus 4 quantity squared. So what we get in the end is 9/4 arctangent of 16 minus 9/4 arctangent of minus 4 squared is also 16. These are the exact same term, 1's plus, 1 minus, so the whole thing is 0. And so what they wanted us to do is, this is another way you can do it, actually plot 1 over x over 1 plus x squared. So plot this. You will see that it's symmetric, and that half of it's above the axis and half of it's below the axis. And when you do that, when you have that, the area below the axis is negative, the area above the axis is positive, and they're the exact same, so they cancel each other. So you can see it when you plot it, or you can do this sort of arithmetic, and you'll see you get the same answer. So 0 is the result. And that will conclude the first section of Chapter 15.